बिल्कुल कोड कर दिया है, ठीक है। आप स्टार्ट कर दीजिए।
So I invite my TA of the course, Suraj Bhan, who is working very hard to help me and in the course as well as to help all the students to solve a tutorial problem for you. So over to Suraj Bhan.
Thank you, sir, for introducing me. So today we are going to solve a problem related to symmetry matrix. We will do a complete analysis of a symmetry matrix. So we will take one example. So this is a symmetry matrix in a cubic crystal. So we will do complete analysis of this symmetry matrix. So to analyze the symmetry matrix, the first step is to take the determinant, and from the determinant, if it is positive or negative, we can tell whether it is a type 1 operation or a type 2 operation. So first we will determine the determinant of this symmetry matrix. So we will solve the determinant for this one and see.
I think you can simply write the value. People can work out.
-1. So here we got negative determinant as negative. So this is a type 2 operation. And type 2 operation in point symmetry is a roto inversion. So now we have determined that this is a type 2 operation and it is a roto inversion. So now our next step would be to determine the fold of this symmetry operation. So to determine the fold of the symmetry operation, we do trace analysis. So and for type 2 operation, trace is minus 2 cos theta plus 1. And from the, sorry for this, from the matrix we can calculate the trace. The sum of the diagonal elements is the trace. So here it is -1. So if we will solve this, theta plus 1, then we will get cos theta is equals to 0 and theta will be 90 degree. So it's a fourfold roto inversion. So now we have got that we have determined the fold of this symmetry matrix. So now our next task is to determine the axis of rotation. So to calculate the axis of rotation, we will calculate the invariant points. So all the points lying on the axis of rotations are invariant points. So let us take, let x, y, and z be a invariant point on the symmetry axis. So this since it is an invariant point, it will not change after the symmetry. It is invariant with the symmetry operation. So our symmetry operation is 0, minus 1, 0, 1, 0, 0, 0, 0, minus 1.
हम्म
X, Y,
नहीं है
Z. And for type 2 operation, the invariant point we take negative. So X, Y, Z. Y, Y minus X minus Z. So equals to minus X plus Y Z.
Suraj, there are some questions and comments in this YouTube channel, so we can address.
Yes.
So am I on the screen? I can't see. दिख नहीं रही नहीं आपकी स्क्रीन में है सर अच्छा लेकिन फिर स्टूडेंट को नहीं देख पा रहे हैं नहीं स्टूडेंट नहीं मैंने स्टूडेंट का कमेंट्स जो अभी दिखला रहे थे हाँ इसीलिए दोनों लगा दीजिए इधर बगल से कमेंट दिखता रहे पूरा स्क्रीन ना भी देखे देखो और फिर यहाँ पर स्क्रीन इस पे आ रहा है और यहाँ पर यूट्यूब में क्वेश्चन Yeah. Yes. So hello, Aman Kumar. I can see your message. I am in part of this session. Although, as I told that Suraj will be solving the problem for you all. Hello to Shelly Singh also. Aman Kumar says there is a question regarding trace of a matrix. So I can see he has a question below. If a cubic crystal, we change the basis to the triclinic and rotate the crystal by an angle theta, does the trace of a matrix will still be unchanged, meaning 1 plus 2 cos theta? Suraj, you would like to respond to this question?
Yes, sir, let me check the question once
Oh,
again.
what did I do?
Here.
Hmm? This is something else. Yeah, here. And there is a something by Sandeep.
So
How do I manage this?
click here, sir.
Hmm? MS Sandeep
Sir,
Parnaik is saying
trace
something,
is-
na? So संदीप only can handle this. संदीप जी ये नीचे का कमेंट कैसे देखना है? अच्छा वहां से नीचे करना है.
So,
Yeah. Good evening, Ajit. We can see your comment. And yes, Suraj, you have a view on that?
yes, so trace is always invariant if you even if we are doing transformation from one basis to another basis. So it will not change if you are transferring from cubic system to triclinic system.
I think I proved this in some video.
Yeah, there
Is
is
that
one
video there?
separate section also that invariant
Mhm.
we have proved
Mhm.
the invariant of a trace.
Okay. If you have that number, you can share with them, or maybe later in the chat.
Yeah, I will share
Mhm.
that.
There is a video, Aman, which where we have proved exactly this, that irrespective of the crystal coordinate system, uh, the trace will always be 2 cos theta plus 1 for a for a rotation, and it will be minus 2 cos theta minus 1 for roto inversion. So we wait for Aman, if you are satisfied, you can confirm in the comment. Otherwise, Suraj will continue with his analysis of the symmetry matrix. Yes, Suraj, you can take over.
So now if you will equate the both the matrices, we can see y equal to minus x is equals to minus y, that is x is equal to y, and z is equal to z. If we carefully look, y equal to minus x and x equals to y, this is only possible when x is equals to y equals to 0. So our axis of rotation becomes 0, 0, 1. But still we have not completed the complete analysis of this symmetry matrix. We need to determine the sense of rotation about this axis. Sense means whether we are rotating this symmetry operation is counterclockwise about that axis or clockwise. To determine to determine the sense of rotation, so sense of symmetry operation, we calculate the determinant of an
If I can interrupt you,
Yes,
I
sir.
think you have solved a similar problem in the solution to one of the problems.
Yes, sir.
But there, although we have found the fold and also the axis probably.
Axis, yeah.
Axis and fold we had found, but we have left this sense. Sense was not required.
Sense was not required.
Sense was not required because it was a two-fold rotation. So for two-fold rotation, whether you rotate clockwise 180 degree or anti-clockwise 180 degree, it's the same thing. So if n is equal to 2, sense is not required. But if n is equal to 4, so that's a 90-degree rotation, a clockwise rotation and an anti-clockwise rotation are very different rotations. So just finding that it is a four-fold is not good enough. We have to decide whether it is 4 plus or 4 minus, or in this case 4 bar plus, because you have a roto inversion now.
Yes, sir.
So 4 bar plus or 4 bar minus. So that's what he is now trying to do.
So to determine the sense of operation.
But did you find the axis before? Okay, you have already
Yeah.
done. Carry on, carry on. I missed that.
So to determine the sense of rotation, we need to determine to calculate the determinant of by taking vector r and the operated r and axis. Here r is any arbitrary vector, not on the axis of rotation. And here a is my axis, and wr minus wr is transformed vector. So let us take 1 0 0 as my arbitrary vector and calculate the determinant. So 1 0 0, and after the transform vector will be 0 1 0. And
can we not reduce this white portion because that is not being used? No?
Yes, all this is coming.
Can you hold this and pull up?
No, it is not going.
Okay, carry on.
And our axis is 0 0 1. If we calculate the determinant, it will come as plus 1 1. This is positive. So our sense of rotation is positive. So it is a counterclockwise. Clockwise rotation. Thus, this W, this symmetry operation, is four bar plus along 0 0 1. So this is the complete analysis of symmetry matrix. First, we determine the determinant, where through determinant we say whether it is type 1 or type 2 operation, and then we we do trace analysis to evaluate the fold of the symmetry operation, and by taking the invariant points we find out the axis of the symmetry operation, and finally to evaluate the sense of rotation or roto inversion, we take the determinant of the arbitrary vector or transform vector and the axis of axis, the axis of axis vector. So this is the complete analysis of matrix.
Thank you, Suraj. Thank you for solving and explaining nicely the analysis of a given matrix. Of course, this is for a point group because this operation does not involve any translation. When operations will involve translations, then we will need to include that also. And then matrix is not sufficient enough, or it doesn't have the capability to represent translations as well. For that, we need affine transformations, and affine transformations are represented by so-called sites operator, where we will have matrix as well as a translation vector. So there will be matrix will operate in the same way, rotation or roto-inversion, but it will be followed by a translation. Of course, this translation which is there in affine transformation sometimes will represent intrinsic translation, as it happens in the case of screw motion or glide motion, where the rotation is followed by translation or a reflection is followed by translation. So in that case, the translation is intrinsic translation, or sometimes translation may be present, but it's not an intrinsic translation. It is present because the rotation is happening not through an axis passing through the origin, but through an axis somewhere else in space. Because once you are in a space group, there can be rotations about many different axes and not only through one fixed axis in the origin. So the translation part of the affine operation represents both the location part as well as the intrinsic translation part. So we will later on we will do, we have not yet done all these things in the video, Suraj.
Yes, sir.
So when we have discussed these things in our video, then later on we will do problems of that kind as well. There are some more comment here. Aman is saying thank you. Sense of rotation is not properly understood. The matrix is becoming too obvious. So exactly what is your doubt, Aman, regarding the sense of rotation? What is the worry? Did you explain the philosophy behind that? That why we so that's why it may not be clear. So maybe you should try to explain why we looked for, because otherwise it will be a mystery kind of thing. So can I take over?
Yes.
And do that for you? Of course, you can also do that, but since I am here, let me do some writing as well. Which is the eraser here. So see, what we are looking for, you have a you have a rot you have a rotation axis, and about that a rotation is happening. Okay. So in your case, it's a roto-inversion axis actually. So when he is selecting an arbitrary vector, when Suraj selected an arbitrary vector, he meant an arbitrary vector at some angle to the axis. He has already found an axis, so he can avoid being parallel to the axis. Why we are trying to avoid being parallel to the axis? Because then the rotation will not have any effect on that vector. So we want to start with a vector which will get rotated by the rotation operation. So if this vector gets rotated, let us say here, and of course, since it's a roto inversion, it will finally come this way. But we want to decide the sense of the rotation. So we don't want to look at the inverted vector, but we want to look at the rotated vector only. So we want to look at this vector. So that's why this minus sign here. such that so this was, let us say this was a 4-bar operation we are talking about, and this is Surajban's vector R. Then this is 4-bar R. But then by multiplying minus with minus, he is getting 4R. Not the inversion is being removed. And then, of course, the last one is the axial vector. So that is this vector here. So he is now looking at these three vectors, R, and this is your minus WR, and A. You can see that if you take the cross product of R and minus WR, then it will be in one direction. If you take the cross product in opposite sense, the cross product will go in the other direction. And depending on whether the axis lies in the side of the cross product, the left-handed or right-handed system is decided. So you know that if you have three vectors, if you have any three vectors, so let us say u1, u2, u3, v1, v2, v3, and w1, w2, w3. These are the components of three vectors, u vector, v vector, and w vector. This determinant will be positive only if u, v, w are making a right-handed system. And a right-handed system means a counterclockwise. They will form a right-handed system only if it's a counterclockwise rotation. So that is the system he is using. Check that. Have I made it clear, Aman? You can comment. You made a comment, the matrix is becoming too obvious. That is not very clear to me. That what exactly you mean by that? That the matrix is becoming too obvious. Means your matrix is simple, you mean? We are lucky that the matrix is simple. In fact, in symmetry analysis, matrices are always simple. Because if you choose conventional basis, and if you choose all the, because you have only this 1-fold, 2-fold, 3-fold, 4-fold, and 6-fold rotations, these rotations in their conventional basis will always give you nice symmetric matrices, always with 0 and 1. So matrices are not so complicated. And as you can see, what we are trying to communicate, that analysis of matrix is also not complicated. Only you have to understand it, the concepts behind that. Otherwise, you are usually multiplying only 0 and 1, not beyond that. Is that right, Suraj?
Still confused.
Yeah. So please try to share in writing. It may be a little difficult, but we will try to see. Yeah, you please do work out, but still, if you can express your confusion while we are here, I'll make, or Suraj will make one more attempt to have a go at it. We are happy with your participation, Naman. We like your questions also on the discussion forum. So please continue the good work. Isn't that Suraj? He is the most interactive person on the discussion forum. Where are you from, Aman? Which institute? Are you a student or a professional? This one-way communication is not good. I'll prefer Zoom meeting to this because they can hear my voice, but I can't get their voice, and I have to depend on the writing. Oh, BHU, that's my alma mater. I'm an alumnus from BHU, so you are my junior. Very, 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 very junior. Oh, that's great. All the best for your thesis. It shows your commitment for learning crystallography. That in this very tough time, I know that submission of thesis is a very difficult period. And in that period also you are taking a new course and making a sincere effort. So I am impressed. Oh, you say that you know me. Maybe I also know you, but my memory has failed me. Oh, good, good, good. So you attended Interfaces in Material Science, the Gyan course, given by Professor Kevin Knowles. Are you working with Professor Basu? Oh, that's good. That's good. Very good to know. So the Gyan course was really useful for you. So you can visit us again. We can have tea together and discuss some more crystallography. Anyone else want to say something? There seems to be quite a bit of lab also. And why Sandeep Pramanik is being shown there? It's expecting a reply or what?
Yeah, we can time.
Hmm? अच्छा 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 वो तो आप ही हो मैं सोच रहा हूँ कोई स्टूडेंट उधर बैठे Yes, if no one has any further comments, Suraj, you want to say something? You can tell them what you are planning in the future videos to come.
Yeah, we are 3D point groups will come in a very organized manner where we will show stereograms for each point groups, and also we will show the equivalent points also, that equivalent symmetry operations that will be there in particular point groups. And after that we will go for space groups, starting from the introducing the space groups, and we will go ahead with all the axes like screw axes and glide planes, and we will also touch the international table of crystallography, and after that we will end this course by taking the tensor concepts. Okay, that's all in the course.
You will not have any party? Final party?
Final party we will celebrate with
Yes, Aman, please go ahead. You have one more question, you say. Please type your question. Let me also thank everyone. My thank you will come from Sandeep Pramanik's ID. He is here to help us with all this arrangement. Because of him, we are having this interaction. So thank you, Sandeep ji, also.
posted one.
Yeah, here is Aman's question. Let's say a plane in some non-cubic crystal. You are very much focused on non-cubic, Aman. So cubic crystal will have some direction HKL, which might be perpendicular or maybe not. So yeah, there is an HKL plane and an HKL direction. They may or may not be perpendicular. Yeah. But how do we know which direction in the real space is perpendicular to that particular plane? The ball is in Suraj's court.
It depends.
No,
Like
you remember we were
we had derived formula for HCP, we have derived.
HCP we derived the formula.
Yeah, for HCP we have derived that for HCP the C every HKIL HKI will be same, but the last part L will be different. That will be 3 by 2 1 by 3 by 2 C by A whole square L.
But in the last tutorial in our offline course, we were discussing some concept of metric tensor as a transformation matrix. You remember?
Yes, sir.
From real to reciprocal. And so we can use that concept here. Let me show. That's a very good question. To find the real space direction perpendicular to a given plane, perpendicular to HKL plane. Now, one thing is clear, that the reciprocal space direction perpendicular to the plane we know. We don't have to work anything for that. That's the definition of the reciprocal space. So reciprocal space direction perpendicular to HKL plane is HKL. Not in real space, but in reciprocal space. So let me put it a star. So the same numbers, but in the reciprocal space. That means it is not HA plus KB plus LC, but this vector is now HA star, KB star plus LC star. We are happy with that. So now all that we have to do, so we know the vector in the reciprocal space. The same vector we have to express in terms of real space. So we really need a coordinate transformation matrix for a vector in reciprocal space, let us say, and it's going to transform into real space. So this is reciprocal. And this is real. But the same vector. So it's actually just a sort of coordinate transformation. But usual coordinate transformation is from one coordinate in real to another coordinate in real, or one coordinate in reciprocal to another coordinate in reciprocal. Here we have a little bit more dramatic matrix, which will transform a vector from reciprocal space to real space. So these are components of the same vector in reciprocal and real. If you work this out, it looks like that it's going to be a very complicated matrix, but this matrix is nothing but G inverse matrix or a G star matrix. That is reciprocal. So this is a coordinate transformation. I didn't do this in video.
No.
Shall we make a video and put this also? Because this concept is missing in our video series.
Yes, that will be a great idea also.
Yeah.
We can take this also.
Yeah. So maybe the next time we are recording a video, we will record a video for this. So with more proper justification also. It's not difficult to show this. If you want, we can show that also. That Y is G star, this coordinate transformation matrix. Okay. But for the moment, let me end with this solution, this algorithm, that HKL was a vector in reciprocal space which is perpendicular to the plane, but you want a direction UVW which is in real space which is perpendicular. Just multiply HKL with the metric tensor in reciprocal space. So this is metric tensor. Reciprocal space, and you will get the direction. So this is, of course, you have said apart from geometrical construction. I'm not doing any geometrical construction here. I am giving you algebraic formulation or an algebraic algorithm to do that. So you have your triclinic, bad triclinic crystal with A not equal B not equal C, alpha not equal beta not equal gamma. However bad it is, you can very happily construct the G matrix, the metric tensor matrix. I have a video on that. Just invert that matrix to get G star matrix. Or you can do it other way around. You can, from A, B, C vectors, you can calculate A star, B star, C star vectors and then find their dot products to construct G star matrix. Once you have the G star matrix, multiply G star with HKL, you get the corresponding vector in the real space. Does that make you happy, Aman? I want my students happy. Learning should be a process of joy. You should derive more happiness by learning new concepts than watching a football match. Because watching a football match, however exciting it is, you are simply an audience. In learning, however difficult it may be, you are a participant. So Aman is happy. So I think we can end with this happiness note. Any other question, Aman, or shall we say bye-bye? There are some few people more I can see who have joined, but they are being very quiet. But I assume that they are also very happy. They are so happy that they don't want to break their meditation. Silence is also happiness. Okay, bye-bye. Thank you. Thank you. Thank you, Suraj, for helping me. And thank you, Sandeep ji. आ जाइए. आप भी participants को thank you बोल दीजिए.
Sir, thank you.
Sandeep ji is always very helpful.
Yes, thank you, sir. Thank you.
आपका आ रहा है कि नहीं?
हाँ, आ रहा है।
ठीक है.
तो ऑफ कर दीजिए।
हाँ. तो और कोई पूछ नहीं रहे हैं. ठीक है. बाय बाय. ओके.
Bye to everyone.
ओके कर देते हैं। एक मिनट। पूछ रहा है कि वो पूछ रहे हैं कि हम लोग नेक्स्ट और भी सेशन लाइव सेशन कर सकते
कहाँ
हैं।
कोई पूछा?
अभी आएगा, यदि इसको मैं रिफ्रेश कर दूंगा तो आ जाएगा सर। कहाँ गया? अभी तो था सर।
चलो ठीक है.
ये है ना सर। We should rather be doing more interactive session। कर सकते हैं सर।
वो तो वही.
इस समय एक ही लड़का जो है वो ज़्यादा